We're going to look at a few other different types of capacitors, including cylindrical and spherical. Um, First of all, a cylindrical capacitor. Now imagine that this is actually a very long cable that looks like, whoops, I've got the wrong control here, that looks like this. You're looking at a cross section here, but in reality it would be a very long cylinder with an inner conductor on the inside like this, and its length would be L this way. The question is we assume that the charge on the inside is positive Q. The charge on the outside is negative Q. So that means outside of this thing, the electric field is going to be zero. And the only place we're going to have electric field is in between the two conductors. Both of these are conductors, and so there's no charge here on the inside, all on the outside. So using Gauss's law, first of all, to figure out what the electric field would be at this point right here, some distance r away from the center of this thing, where a is the radius of the inner part, b is the radius of the outer part. If we use Gauss's law, again, we're going to use sort of a cylinder that's built inside of this thing. And most of you would be comfortable at this point saying, oh yeah, it's just going to be passing through the skin of this Gaussian surface. And the area of the skin of that Gaussian surface is just going to be its circumference, 2 pi r, times the length, L. Charge inside is going to be Q over epsilon naught. And so we discover the electric field in between the inner and outer conductor is going to be Q over 2 pi r L epsilon naught. Notice the L does not disappear this time, but don't worry about it. How do we figure out now? Remember the process for finding capacitance. We first find electric field, then we integrate that to find the difference in electric potential, and then finally we plug it into the capacitance equation. So to find out electric potential, we're going to integrate it. And the only region that there's a field is between B, that's this point right here, and A, the inner radius, these two numbers right here. So negative integral of the electric field from down here that we just found. And since I'm using R here, I'm going to call this dr up here. Limits integration from B to A. If we do this, unfortunately, everything in here is a constant except 1 over R. And hopefully you remember that the integral of 1 over r is natural log of r. And so we keep the negative sign, it becomes this. Plugging in our limits, and this time I'm going to leave them in there. And you might say, whoa, wait a second, you reverse the limits. Yeah, it's actually negative of this minus the negative of b. But in that case, negative of a negative becomes positive. So I immediately rearrange these two. And now a small trick. If you remember, if you've got two quantities here, we can factor out the Q over 2 pi L epsilon naught from both terms, but then we have ln of B minus ln of A. And I'm hoping you remember back from algebra or algebra 2 that that's equivalent to the ln of B divided by A. So here is our potential between the outside and inside. Last step, to find the capacitance, we just have to plug it in. So the charge is just going to be Q, the charge on one of the two plates. And then the potential from over here, we're going to plug that in for V. It gets a little ugly. Good news is Q cancels, but we end up with this expression right here. And this is the definition of the capacitance of a cylindrical capacitor. Notice that it is proportional to the length of the capacitor. And it also depends on the inner and outer radius of the two conductors as well. So, a story. Now, first of all, you might say, wait, cylindrical capacitors, why would we ever have these? Well, there's a good story here. Back in the 1850s, it was sort of like the big space project of the time. They laid a cable from London all the way to New York City across the Atlantic. It was by far the longest cable ever produced. And when they first tested it, it completely baffled the engineers. Why? Because they knew it was connected electrically, because they could actually connect the battery to one lead, check, and it would light a light bulb at the other end. They had planned at certain times And the other side, you could put a battery on it and it would light a light bulb the other side. So no shorts, no breaks. It actually worked perfectly fine. But when they tried to send a message across it, it was almost impossible. When they tried to send a message on it, it simply did not work. Um, and it was completely confusing. It was another physicist at the time who actually realized, it was somebody called Fourier, who actually realized, wait a second, you've just made the world's largest cylindrical capacitor. If you think about it, if you look at the cable down below, it had an inner conductor and a bunch of insulators, and then an outer metal conductor as well. And it basically became, because of the length, and remember the equation from the previous one, the length was much longer than anything else. And so, to send the message congratulating the opening of it, the 98 words took 16 and a half hours to transmit by Morse code. Why did it take so long? Because they had accidentally built the world's largest coaxial capacitor. Every time they pressed the key in London, it would take a very long time to charge up this capacitor, which is designed to store charge, and then it would take a very long time for it to discharge on the electromagnet on the other side. So each dit and dash took an incredibly long time to charge up and discharge this very long transatlantic cable. In the end, they kept raising the voltage to the point where it became dangerous to become a telegraph operator on this line. But by doing larger voltage, larger potential, it would charge more rapidly. And by putting a larger load on it, would discharge more rapidly. In the end, they pushed it so hard, they eventually reached what's called a dielectric breakdown, and it actually shorted out under the Atlantic, which was the end of the cable. The other kind of capacitor I want to talk about is a spherical capacitor. And again, you might say, wait a second, where in the world would we ever run into one of these? Well, hailstones from thunderstorms actually have alternate layers of positive and negative charge as the hailstorms form as they fly up and down inside the thunderstorm. And so it's actually a fairly common natural phenomenon. But in this case, not very common in everyday life. But let's talk about it real quick. Same kind of situation, except this time this is not part of a cylinder. This is actually a sphere. And we're going to use the same kind of thing. The inner sphere is charged to positive Q. The outer one's charged to negative Q. And the question is of course, what's the electric field in between the two halves? Electric field on the outside, again, is 0, so we don't have to worry about that. But we do need to figure out what the electric field is right here. Whoops, sorry, wrong spot. Right here at a distance r away from the center. If we do that, very, very similar in a lot of ways, we're going to do that. If we calculate that, we'll discover, oh, hey, that's strange. It's the same as what we had, almost what we had before. Actually, not quite the same, but it's the same as electric field around a point charge Q. If we calculate the voltage this time a little bit more friendly, again, our limits are B to A. But we integrate this, everything's a constant. Integral of 1 over r squared is negative 1 over r. So it simply becomes this, same limits. Plugging in our limits, A minus B. Unfortunately, you're like, oh, it's really simple. Just factor out the Q over 4 pi epsilon naught. Yeah, you could. But to subtract these two fractions, I need a common denominator. And hopefully you can see in this case, you can multiply the first one by B. So you'd end up with all that over AB. And multiply the other one by A. So this would be over AB. And then you could factor out the rest, and you'd end up with Q times B minus A over 4 pi epsilon naught AB. Finally, the capacitance. You just have to plug it in. So the charge is Q. The voltage we just figured out is that. And if you solve this, it comes out something like this. Not super pretty, but hopefully you can sort of recognize, okay, yeah, I could come up with this. I could do this myself. Just a real quick note, if you let the limit as B approaches infinity in this one, in other words, if you only had an isolated conductor with no other one, Believe it or not, that does have a capacitance. You would just have to integrate the electric field all the way out to infinity. But we could also just use this equation. And if you took the limit of this as b approaches infinity, you would discover, and I won't do the math on this one, that it simply becomes this. And you might actually recognize this equation because that's the one we actually came up with when we started this chapter and looked at just a single isolated charged sphere of radius r. But just to show that this is consistent. The next part of this chapter is capacitors or capacitor networks. That is where you've got multiple capacitors connected together in various states. First part I want to talk about are capacitors in parallel. Parallel means they're side by side. So here's one capacitor, the leads for the top one, and they're connected side by side to the leads of this bottom capacitor. This is a parallel plate capacitor with an area of A and a distance between the plates of D. The same thing is true for this one down here. It's also A separated by D. The question is what's the total capacitance of this? Well, we know the capacitance of one of them is just given by this equation. Remember, for parallel plate capacitors, area of one of the plates times epsilon naught all over D. So it turns out, and kind of watch this animation, this is equivalent to this, where it's basically like if you put them, connected them together, you'd end up with a total plate area of 2A, twice the area of that, but the distance between it's still D. Based on that, if A doubled, what happens to the capacitance? It also would double. In general, it turns out you just add up the capacitances of each of the capacitors that are side by side or in parallel. It's fairly simple. And you might say, what's the dot, dot, dot? Well, as many capacitors as you have. For capacitors in parallel, the voltage across to one, or the electric potential difference of one, has to be equal to the electric potential difference across the other one. Why? They're connected together here, and so the change of potential here has to be the same as the change of potential here, even when they're separate from each other, like before I drew them together. You can also write this in sigma notation because it looks cooler. Total capacitance is just the sum of each of the capacitors. So take a look at this one. What's the total capacitance of these three capacitors? Well, if you notice, they're all connected side by side, where the leads of all three of them are connected together up top, and the other leads of all three of them are connected down below. So what's the total capacitance of this? Well, I should actually do a little bit more on this one. I didn't do much of it. Total capacitance in this case is simply going to be the sum of those. So the total capacitance, I guess I probably could write it out, is going to be 2 microfarads plus 1 microfarad plus 1 microfarad, which is going to be 4 microfarads. And I'm going to do this first one a little bit slow, just so you can sort of see it. Because the next question on this one, it's 4, believe it or not. 4 microfarads is the answer to the first part of it. But then it asks, what's the voltage and charge on each of these capacitors? Well, let's do the voltage first in this case because it's actually easy. You'll notice that all these leads of these capacitors are connected to a potential of 12 volts. And the bottom ones are all connected to 0 volts. So what is the voltage on each one of these capacitors, or voltage across them? It has to be 12 volts. And if you're not seeing it yet, maybe write it up here. Wires don't change potential. And so all of these points on top here are connected to 12 volts. They're all going to be at a potential of 12 volts. And all of the ones down here are connected to 0 volts. And if you look then at what the potential difference is across each of these capacitors, they all have to be 12 volts. Again, slight apologies. The variable for electric potential is V, and the abbreviation for the unit for electric potential, volts, is also V. So don't panic here. The potential is 12 volts is what that statement basically means. And now we get the question of though is what is the charge? And you might say, whoa, wait, how do we figure out the charge in each one? Well, if you remember, capacitance is defined as, whoops, that's interesting, is defined as the amount of charge per voltage. Or rearranging that, C times V is equal to charge. Since we know the capacitance on each one of these, in this case 2 microfarads, we can very quickly figure out the charge. 2 times 12 is going to be 24, and I'm going to leave it in the unusual unit of micro. In this case, the charge is going to be in coulombs. For this one, again, I'm going to do C times V. Capacitance is 1 microfarad times 12 is going to give me 12 microcoulombs on this one. And you can probably by logic figure this one out as well. This one's also 1, and so doing C times V, also 12 microcoulombs. Just as a side note, not that you need to see it right away, you could have also figured out this a little bit by basing on this. This whole capacitor network is equivalent to 4 microfarads. If you hook it up to a potential difference of 12 volts, how much charge would flow in? Well, you should discover that it's going to be a total of 48 microcoulombs. 4 microfarads times 12 volts. And so what happens on this? Charge is never created or destroyed, just like mass in chemistry. So we have 48 coming in from here, microcoulombs. And when we solve that first capacitor, you actually know that when it reaches this junction, we know that, it's really not drawing very well, that 24 go down this way. Since charge is never created or destroyed, how did I know it was 24? Because that's 24. So how much went through the junction this way? Well, we started with 48, 24 went down this way, leaving us 24 up here. And then at this next junction, we know we have 24 coming in, and then it splits up again, and we know that 12 are going down this way. Why? Because we already solved that capacitor, 12. Since we had 24 going in, and I won't write microcoulombs, I guess I will. And we have 12 going that way, you can immediately know that 12 microcoulombs must have flowed to this last capacitor. I call this physics Sudoku, or at least network Sudoku, because you can actually solve it multiple ways. All right, let's take a look at another situation. When capacitors are connected in series, they must have the same amount of charge on them. So the amount of charge that flows in over on this side, the same amount of charge is going to leave this plate and flow over to the next plate, and the same amount of charge is going to leave the far plate and flow out. So let's say we have these capacitors and they both have an area of A and a separation distance of D. What is this equivalent to? And I'm just going to erase this so it doesn't get too messy. Well, you can think about shortening this wire in between here over and over again, and you would discover that it's equivalent to, and I took out sort of the middle plate here, it's equivalent to basically a capacitor of area A, but twice the distance between it. Because I'm doubling the distance between the two plates, what does that do to the capacitance? It makes it half as large. And so the equation for capacitors in series, where you have them one after another, it's this equation. 1 over the total capacitance, I'm going to write it out just so you can see it, is equal to 1 over the first capacitor plus 1 over the second capacitor, or capacitance, I should say, plus 1 over the third capacitance, yada, yada, yada. Forgive me, my first one, my plus dot, dot, dot. And again, you can write that in segmentation up on top. That looks a lot nicer than what I just wrote right here. Let me fix this because it bothers me. 1 over capacitance 1. And it turns out it's a fairly nice idea. So take a look at this one. what's the capacitance of this series of capacitors? Um, if you plug it in, 1 over 3 microfarads plus 1 over 2 microfarads plus 1 over 1 microfarad, you're like, oh, it's easy, 1 over 6. No, remember for fractions, you got to get a common denominator. So we're going to convert it, the common denominator in this case is 6 microfarads. If we add that all up, we'll discover the total capacitance is 11, or actually 1 over the total capacitance is 11 over 6. What does that mean our total capacitance is? It's the reciprocal of that, or 6/11. Why again? If you're like, well, wait a second. Yeah, it's because this sum is the reciprocal of the total capacitance. So when you get this final answer, remember to flip it. All right, we got that. Now, what's the charge and voltage on each capacitor? To answer that one, we've got the total capacitance of these 3 capacitors. And maybe I should erase all this other stuff here for a moment, just so it gets out of the way. We know that these 3 together act like a single capacitor that would have this total capacitance that we just calculated. So what can we do with that? Well, we can actually use the definition of capacitance. And we know, again, if we rearrange that, the charge is going to be equal to C times V. In this case, we know our capacitance is this number right here. And what voltage are we applying to our equivalent capacitance? 12 volts. And so if you figure this out, we'll discover that the total amount of charge that's going to flow into this circuit is going to be, and my apologies for the really hideous fraction, 72 over 11 microcoulombs. And I'm not going to write that too much. But if you remember what I just told you, that same amount of charge is going to flow out of that plate and go onto this plate. And the same amount of charge is going to flow out of this plate and go onto this plate. And the same amount of charge then is going to flow out of here. This plate will become positive, this one negative, positive, negative, positive, negative. So we can actually then go ahead and put down the charge on all 3 of these is going to be the same. The same amount of charge that goes into the 3 microfarad capacitor is going to be distributed between all of them. And then the question is, well, what's the voltage on each one of these? Let me erase that for a second. Well, if you remember, whoops, going the wrong way, you can rearrange this same equation down here and actually solve it for voltage. If you do that, you'll discover voltage is equal to charge over capacitance. We know the charge on this 3 microfarad capacitor, and so we can actually solve this one by just taking that divided by 3. If we do that, we get this rather hideous voltage of 2411 volts. I know, I'm sorry. And then for the next one, we can do the same thing. This charge divided by the capacitance, 2, gives us 32 or 36 over 11 volts. And then finally, the last one stays at 72/11. The interesting thing about this, if you add up these 3 voltages, you'll discover that it adds up to exactly 12 volts, which is what we would expect because we know the difference between the 2 endpoints has to be 12 volts between here and here. And so the voltage across each one of these together adds up to 12. You might have to actually check that to believe me, but it really does work. These next 2 and the last 2 slides I want to do are slightly more complex ones. Are these capacitors in series or parallel? The answer is yes, they are. In fact, these top 2 are side by side. The 5 microfarad on top and the 10 microfarad are in parallel with each other. And then those 2 are in series with this 15. Their ends are connected to the other end of this one, which then goes on to the battery or voltage. So first thing, what's the total equivalent capacitance? I'm going to start this like it's a math problem. And I'm going to do the 2 capacitors that are in parallel first. Why? Because I need to find that, and I know these then are in series, end to end, with the other 15 microfarad down below. Solving this one, we got to do a little math. Actually, not much math. Since it's in parallel, we just have to add them together. 15 microfarads. I like that part. Now, What's the total capacitance of this? Well, this 15 microfarad is in series with this 15 microfarad. So I've got to do the 1 over thing, and this one I wrote out. Gives us that, and we just have to take the reciprocal. And so the total capacitance of this circuit is 7.5 microfarads. You're like, okay, got that. All right. Typically, we always find the total capacitance first whenever we're doing a network. Why? It simply makes our lives so much easier down the road here when we do this. Now, we're ready for the math part. I always want to know how much charge is flowing into the network. That is literally my big question. I know that charge is going to split up, but we'll figure that out later. Part of it's going to go through this junction. Sorry, it's really hard to see. And part of it's going to go down this way. Maybe color that in a little bit better. And then we've got going here, goes down this way. And then this charge here is going to combine both from this side and go down to this capacitor down here. And then this capacitor, that charge flows back to our voltage. Whatever the charge is here, that's going to be the charge coming out down here. You might say, oh, so is a Q here and Q here? No, because it's going to split up at this junction right here. But we can figure out the total charge. Plugging in the total capacitance of our whole capacitor network and the voltage, 30 volts, we can discover that, 225 microcoulombs are going to be flowing out of the power source and charging up our network. You're like, great, I know that, but how do I know how this breaks up here? Is it going to break up equally? Probably not, because it's two different capacitances. You're like, oh, great, I'm stuck. Well, believe it or not, we do know the charge on one capacitor. Why? Because after it breaks up here, it recombines, and all of that charge is going to end up on these two plates, because it has to go back. So we can immediately tell us that the charge on this capacitor is 225 microcoulombs. And if we do that, we can figure out the voltage. The voltage is just charge over capacitance, if you remember from the previous slide. And that'll tell us it's 15 volts. That means if you hooked up a voltmeter between these 2 points right down here, it would literally read 15 volts between these 2 points. Now, I'm just going to define this point right here as 30 volts. This point down here is 0 volts, which means if you read 15 volts between this is at 0 volts, this point right here has to be at 15 volts. Which means these points both down here would be at 15 volts, or actually these entire wires here would be at 15 volts. I'm just going to draw the points down here. And if that's at 30 volts, that means this point right here has to be at a potential of 30 volts. And so does this point right here. And you're like, oh my goodness, you're drawing so much stuff on here. Yeah, but believe it or not, take a look at this. What's the potential difference across this capacitor? We've got 30 volts here and it's down to 15 volts here. What's the potential difference? Well, hopefully you should recognize, I did that one first. The potential difference here between 30 and 15 is 15 volts as well. So the capacitor, the voltage across here is 15. Warning, it's not always the same. Like here we have 15 and here we have 15. This is accidentally the same simply because the total capacitance here is equivalent to the total capacitance down here. But you can use the same logic about voltage. And so we know the voltage across the other one has to be 15 volts as well. And now we can use that to actually figure out charge. Charge is equal to capacitance times voltage, just taking our capacitance equation, rearranging it. So in this case, 15 volts times 5 microfarads gives us 75 microcoulombs on that one. On this one, capacitance is 10, voltage is 15. It's going to give us 150, and I'm leaving the micro in there, microcoulombs. Notice that the sum of these two is going to give us, when it recombine down here, it's going to give us the 225 that we need down there. I know. It was pretty tricky, but you can watch this again. And now I want to do one of the more complex ones from your homework tonight. This is from the capacitor worksheet. This is question number 7. This one is a fairly complex one, but if you follow through on this one, the first thing we always have to figure out is the equivalent capacitance or the total capacitance of all these capacitors. Oh, by the way, the little red marks and blue marks are from the program I used to design this. It actually puts low voltages on each point. So, first thing, how do we solve this one? These capacitors are both in series and parallel. Well, if you look at it, these three right here are connected end to end to end. These three are in series. And so if you solve these, doing this equation, you'll hopefully quickly realize it ends up being 3 over 1 microfarad, or taking the reciprocal of that, this is going to be 1/3 of a microfarad. Run the math through yourself just to be sure. And now that is part of this much larger network. This, in sort of blue outline, this whole thing is equivalent to a capacitor that is of that particular capacitance. How is that connected to the other ones? So I want to do blue here. Well, this, if you think about, here's the end of this bunch of capacitors. It's connected to this end of this capacitor and this other end of this capacitor. And this end's connected to this end and this end. These three capacitances are all in parallel. You're like, 3? Yeah, we're treating this blue dotted area as one capacitor of this magnitude. So what's the total capacitance of everything inside of this gold shaded region? It's just going to be 1 plus 1 plus 1/3, or 2 1/3 microfarads. I know that seems a little bit much, but just hang in there for a second. I'm going to erase a little bit of stuff here just so it doesn't get too confusing. And now we're actually able to answer a few more things. So what's the total equivalent capacitance? Answer is it's 2 1/3 microfarads. And yes, you could also write that as 7/3. I guess I'll do that. Microfarads. And now we're going to do the same trick we did before. Why? Because we know that when the charge goes in here, we can figure out how much charge comes from the power supply. We can figure out how much goes into this capacitor, how much goes through this junction. At this junction, how much goes through to the other capacitors, and how much goes down this way. We're going to do the same trick we did before. But first of all, we got to figure out the total charge that's going to flow into this thing. Using this equation up here, plugging in those numbers, the total capacitance times the voltage we're working with, gives us 28 microcoulombs. That means there is 28 microcoulombs flowing in to this whole thing. And now you might be saying, oh, great, but how do I figure out the rest of this? Do we know anything about these capacitors? Well, all of these points, since they're connected directly to electrical potential of 0 volts, are at 0 volts. And all these points up here are connected to the 12-volt potential line. Could you please tell me anything about any of these 1 microfarad capacitors? And I'm hoping you see it. These two right here are both connected across. They go from 12 volts to 0 volts. That means the potential difference across these two capacitors has to be 12 volts. So I can actually do this. The potential on that one has to be 12 volts. And if we use Q equals CV, you should discover, oh yeah, it's going to be 12 microcoulombs. Which means we can now say, all right, whoops, I'm in red. 12 microcoulombs from this junction must go down to charge this one up to 12 volts. Which means we've got a remainder of 16 microcoulombs going this way. Well, out of that 16, how much goes down to charge up the next one? Well, we can do the same Q equals CV trick. We know the voltage on this one's also going to be 12 volts. And so by the same logic, it's going to be 12 microcoulombs going down in this one. And now that we've done that, could you please tell me how much charge must be going through that junction? 16 microcoulombs comes in, 12 goes down this way. Charge is never created or destroyed. It means that 4 microcoulombs have to be going off this way. And since when you have capacitors in series, any charge that comes in one comes off the other side, goes to the next plate, which forces the same amount of charge off the next plate, which goes on the next plate, which forces the same amount of charge out of there. Based on that logic alone, we can now say that the charge on that one's 4 microcoulombs, and the charge on that one's 4 microcoulombs, and the charge in the bottom capacitor also 4 microcoulombs. And if we rearrange this equation, voltage is equal to Q over C. We know the charge. We can very quickly, and we know the capacitance. 4 microcoulombs divided by 1 microfarad means the voltage on this has to be 4 volts. The voltage on this one has to be 4 volts. And the voltage on the bottom one has to be 4 volts. And we have completely solved this one. I realize it's a little messy. I probably should erase all my extra drawing on this one, which might make it a little bit easier to see. But the key here is we simply always figure out total capacitance of the circuit, figure the total amount of charge that goes into the network, and then once you have that, you can go ahead and figure out what you can figure out. In this case, we knew the voltage across these two were 12 volts. We knew the capacitance. We could figure out the charge in each one of these. We could figure out what remainder of the charge went over to these. Once we knew that remainder charge, we could figure out the voltage on these. And you're going to do the same thing with some circuits tonight on that capacitor worksheet. This is one of the harder ones. The last one on it, number 8, is also fairly challenging. I think I gave you an answer key, so don't panic too much.